Hey, I'm John, and I'll talk about evaluation of Speedup and energy with specifically the Oscar multigrain parallelizing compiler. But before I begin, I just want to make a quick note of how I know Vivek. I met him today, so it's a very short time. Yes. But my advisor, Hironori Kasahara, has worked with him and has met him for like quite a long time, since IBM and back in the day. And he has, when I work with Seda, I'd often ask, like, we have the big Oscar compiler, like, how does this function work? How does this module work? And he'd be like, oh, this was written by some of our former members, but they're now in Vivek's group. So he's taken some of our talent, if you will. So, but no, I've heard a bunch of good things from him, from my advisor, so just a little tidbit. So I'll be talking about the Oscar automatic compiler, parallelizing compiler. It uses multigrain parallelism to speed up and also provide energy reduction. Basically, automatic parallelization and last level cache optimization is what I'll be looking at in this talk and also in the paper. The focus kind of being that we want to minimize energy consumption while maintaining runtime compared to OpenMP. So kind of the context of why we're looking into this for research is that computers are more or less everywhere. There's a constant energy demand from them. But more specifically, data centers take massive amounts of energy to more or less function. With the rate it's scaling, it's kind of like data centers themselves are going to need their own power plants. And instead of using fossil fuels and nuclear energy, which we kind of want to kind of deviate away from. If more or less we want to try and focus on sustainable computing. So just a few more background slides. Just want to do a quick overview of one of Intel's architecture, Icelake-SP, which I'll be focusing on a little more later. What I just want to kind of highlight is the mesh interconnect network, how the cores are more or less connected, if you will. More or less, each core has a shared 1.5 megabyte L3 cache, which more or less any other cores can kind of communicate with. I know, I think it was done for latency involved for communicating with a different core, I think it was about 40 nanoseconds, 50 nanoseconds for the furthest core. And it's just a mesh interconnect where every core is kind of connected, or it can be connected going through other cores to the left to right or up to down. In comparison, there's the AMD Zen 4 architecture, where there's more or less a central I/O die, as well as different chiplets. And the chiplets might have 8 cores each, and they might have 16 to 32 megabytes of L3 cache for that specific chiplet. And if there's multiple chiplets, let's say there's 8 cores each, and if there's a 16-core processor, more or less, there's going to be some remote and local memory accesses. So I'm going to turn my attention to the Oscar compiler. So I'm just going to do a quick overview, if you will, a basic overview of how the Oscar compiler kind of functions and works with code. So Oscar is an automatic parallelizing compiler. It is a source-to-source conversion in that, let's say we have C, C++, or Fortran code. We could insert it into Oscar, and we will get C, C++, or Fortran. Whatever we put into it, we will get that code back. And that output code is able to be compiled by various different compilers, such as GCC, Clang, Intel compiler. It just needs to follow the spec for this given language. Most of the features that I'll be talking about later are for optimization will be done in the middle pass by Oscar. So how Oscar operates, it basically takes tasks, or coarse grain parallelization. It takes different tasks of code, let's just say assignments, loops, just normal operations, and it turns them into different blocks. These blocks will be used to kind of schedule and do dependency analysis to kind of see how the program flow is defined. In these examples, I have OpenMP directives, but Oscar does not require them. It can just take a sequential program and automatically parallelize it at the same time. So it supports, and it's not limited to OpenMP directives, for example. It exploits loop-level parallelism. It can do sums and reductions in its own way, and it has more than just these 3 examples of how it determines blocks. With these blocks of code, it will do data dependency and control analysis to kind of see how they interact with each other, and it will construct a macro task graph. More or less, this macro task graph is indicative of the actual program, but these macro task graphs can be made of functions themselves depending on the complexity of them. So we can kind of have we can define the grain of how much we want to see the macro task graphs and how they operate. With these macro task graphs, the scheduling occurs, as well as the optimizations. So just in this case, one of the features I'm looking at with Oscar is some of its optimization for cache and data localization, specifically for last level cache optimization. So on the far left graph, for example, we have like a normal macro task graph, if you will. But let's say for a specific target system, we know the cache size and like the data size, and we can kind of define those cache groups to kind of make cache lines that fit this specific cache of the target's device. And depending on the array or the program we're compiling, we can kind of split those cache interactions up into different groups. So in a normal program, it might just flow down and do things sequentially, top to bottom, if you will. But instead, during scheduling, we can kind of focus on like a specific data localization group at the same time. So for example, the green line, we can kind of just target down this before we start like the red line or the yellow line or the blue line. So we can kind of keep the cache on the device localized to prevent more or less cache misses and other issues in that regard. So with that information, we can schedule. And just for this example, we have two PEs, 0 and 1. And we can kind of see like we can get more or less from execution flow, like 1 starts on PE 1, 12 starts down here, if you will. It's just the next iteration that needs to happen. But we can kind of see like green is clustered in a group, yellow is clustered in a group. It manages data dependencies. Of course, this is more or less coarse-grained task scheduling, and it has its own version of first touch and automatic thread binding in that regard, depending on what you want to, whatever the program benefits from. So to kind of go on with the evaluation of Oscar and these features, I'll be looking at benchmarks on Intel and AMD systems of what I kind of spoke about before. More or less, the big thing is Intel has its own mesh network. AMD kind of has its I/O die with the chiplets and the CCXs. More or less, the main thing I want to show is the L3 cache, where Intel has 1.5 megabytes shared per core, while AMD kind of has their own blocks, the local block and the remote CCX block of 16 or 32 megabytes. In this case, it'd be 32 megabytes for each CCX. Both processors have 16 cores, and I'm just running this on Ubuntu and hyperthreading disabled. This is not exactly a comparison of Intel versus AMD, but it's more of a characterization of how Oscar performs on these Intel and AMD systems. And just a quick note, I'm using RAPL and hardware registers as well as like some of the cache registers to get performance results. Some of the benchmarks I'm looking at is some of the kind of older ones is the Spec 2000, is we kind of just have that in part of our internal suite. But also I'm looking at the NAS parallel benchmark, specifically the block triangle BT, scalar pentagonal SP, as well as conjugate gradient. More or less, these benchmarks were run 25 times, and I'm looking at the median values. And Oscar kind of is a source-to-source parallelizing compiler. I'm just going to use GCC, at least in my evaluation here, to look at the results, or compile the output code to look at the results. So looking at performance at Intel, there are 3 different benchmarks run. Blue would be OpenMP, or the sequential program. Red would be Oscar. And Oscar, we can kind of determine what special features we want. So there's another one, Oscar, the green Oscar plus cache optimization, which is kind of the data localization and trying to minimize cache misses at the same time. So just one more note for Swim and Art. Since it's kind of an older benchmark, only sequential program was provided. So if you see the blue line is only for 1 core or 1 PE, for example, because that's all there is. But more or less, we're able to see for relative speedup on Intel that Oscar is able to accurately, or it's able to automatically parallelize these programs to get a decent relative speedup. We can't see ART kind of does saturate, the same with SP does saturate, but I will come back to that in a moment. But we can see, like specifically Swim and CG2 have really good results where we can see 10 times speed up, and at the same time, if we look at the lower half, we can see that energy is reduced 80% on some of the best case runtimes. But that is kind of known that with an increase in runtime, or like by improving runtime, energy will be reduced. It is interesting to note that in a couple examples, like we can see saturation occur, such as on the ART and CG, where at a certain point, there's too much overhead from parallelization and energy starts to kind of less increase at the same time.
The bottom diagram,
yes.
Lower is better, right?
Lower is better on the bottom diagram, that is correct, yes. Higher is better on the upper diagram. So this is just a very similar slide. It's just AMD. Kind of the trends are more or less the same. One thing I do want to point out, though, this is the same on the Intel, but it's a little more apparent on AMD, is for the test BT. We can kind of see that OpenMP is performing better than Oscar in sense of runtime. But that is kind of a note as I was trying to minimize the energy usage while trying to meet and maintain the runtime, which the runtime was not able to be maintained, but that's more of an issue of how Oscar was set up to interact with BT, where how Oscar can kind of, more or less how we determine, with the macro task graph, it's not appropriately managing the subroutines, which I do need to optimize for later, but that is kind of why it is a little bit worse in runtime, but it still provides less energy than the OpenMP for the equivalent core count. So looking at OpenMP, like a comparison of Oscar with cache optimization to OpenMP, we can kind of see the energy reduce more or less change, if you will. So we can kind of see on BT, CG, as well as maybe for 1 PE, 4 PE, 8 PE on SP, that more or less we're able to reduce energy compared to OpenMP. However, I would like to note, like for 12 PE and 16 PE, we see much greater results, maybe even 8 PE to an extent for SP, but those are more of an issue with OpenMP not scaling properly as we increase core count, where more or less we can see OpenMP has a slowdown as well as energy increase, more or less because it hit the saturation point. More or less, Oscar was able to find a couple bits more parallelization possible, so that's why it just performs better, and those are not exactly real. They are real results, but that's kind of the cause of them. So looking more into a specific case on conjugate gradient, we want to see how much the L3 improved some of the performance. So with the same colors, we have Oscar as the blue. We kind of have red being like, or OpenMP is blue. We have Oscar as the red, and we have the cache optimization along with Oscar as green. And we can kind of see, looking from red to green, that by using these cache optimizations and data localization, we can kind of isolate the L3 miss rate improvement and correlate that specifically to a total energy reduction. And of course, that energy reduction is coming from the improved runtime, if you will. So on Intel, we can kind of see a 0.4% L3 reduction, improved runtime, just how it's working, and it's correlating to a 4% energy improvement, and 0.73 on AMD, which is quite a bit more on energy or energy and runtime respectively, kind of more to how, maybe not volatile, but like how more robust the AMD, or how more complex and how it impacts the AMD architecture, if you will. Yeah, so one thing to note is I am showing an example on CG, specifically for 16 PE, but this trend with the clusters and how like the things moved was also very similar for the other tests. One thing to note also is Intel, we can kind of see the distributions are a lot more centered, if you will. And AMD, they're kind of more spread out. I was able to find that this is more of a situation where on AMD, the CCXs, when we go over 8 cores, there is some CCX communication involved, which plays into the latencies. When we went down to 8 cores and isolated more or less all the processes onto one CCX, they clumped up and were very similar to Intel's in the distribution sizes. So overall, this is the Oscar compiler, and it's able to get various different speedup results and energy optimization just due to automatic parallelization, and we're kind of able to see the effects of the L3 cache improvement alongside it. So some of the future research involved into this, or why this was done, is we're looking into dynamic voltage frequency scaling, but we want to try and get the most performance out of what we could through sequential and improvement, or we wanted to get the most we could out of runtime improvements before we applied dynamic voltage frequency scaling. So we'll be looking into that in the near future. So thank you. Let me know if you have any questions.
Just curious, you mentioned using the first touch. Do you know if that changing that has any impact on the performance, or if there was some input from profiling of the programmer?
Yes.
Which spinning would be better? Is there any room over there for performance improvement?
So we had like a dummy cycle before we did first touch, if you will, to more or less first touch the data onto the correct cores. We didn't. It's been a while, but there was definitely an improvement in doing first touch before we actually started benchmarking the data. I do know maybe it was like a 5% to 10% difference, if you will. That's kind of more or less the first touch happening within the actual main loop. But on OpenMP, we saw the same results, and in Oscar, we kind of have it automatically doing the same thing. It also kind of had the same results. So first touch definitely did help, but that is kind of, I'm using first touch for both OpenMP and Oscar. So it's kind of parity, if you will, in that regard.
Great talk, yeah, thank you. So does Oscar do any vectorization, or is there a backend compiler supposed to do so?
So Oscar, we have vectorization in place for some of the, at least for what I'm looking at here, it's not what you would consider vectorization. We are processing things. It's more or less going through the rate and kind of monitoring the data throughout the whole thing and manually assigning it through its own API directives of how we're going to vectorize it, if you will, in its own method. There are also works right now on how we're vectorizing it for like accelerators as well, but more or less it's all in the same core and it has its own internal vectorization, if you will. All right, thank you.